Well, today is the big day. We're going to prove something about the Euler-Mascheroni constant. We've talked about this before. I've talked about it in a previous video. I'll leave a link to that. And in the previous video, I just described what it's all about without proving anything. So today we will prove some things. We will prove the existence of gamma as a limit, and we will derive this limit expression definition of gamma. We're going to do it rigorously. And all this is a really beautiful example of classical analysis. And to do this, we need a few things. We need some results about the Hn, or 1 over n harmonic sequence, and the areas underneath the curve y is 1 over x. And I did that in the last video just before this one, so I will give you a link to that. You should watch that. I'll review this just a little bit in this video, so maybe you don't need to watch it. But if you want to see the proofs of these things, yeah, watch it. And we need the alternating series theorem, a famous theorem proved by, I think it was proved by Leibniz, maybe. And this is a very powerful theorem because it's very easy to construct an alternating series that converges to a limit. And we will exploit this to find an expression and to prove the existence of gamma. So I've done the entire proof of this theorem, and I did it in 2 videos. And I'll leave the links to those videos in the description box. And you should watch those too. It's a very great theorem to know, very useful in classical analysis. All right, so let's get to this. First, let's have a look at the alternating series theorem. Here I have my alternating series, and I can write it in an expanded form like this: A1 minus A2 plus A3. And so on, minus. So the evens will have a negative and the odds have a positive. And I can define my partial sums. Little s n is the sum k is 1 to n minus 1 k plus 1 ak. So that's the first n of these. And I can also define s2n. This is the even number, even partial sum. So this is the partial sum of the first even 2n even terms. So let's see if I can express that clearly. Okay, it's the partial sum that has an even number of terms. I take the first even number of terms. Okay, and I can also do odd partial sum. So I can see that over here. This has 2 terms. That would be an even partial sum, and this one here, that's an odd type of partial sum. Okay, so this theorem says the following. If I have these conditions, the first condition is that all my ak are greater than 0. And the second condition is that my ak is monotone decreasing. So what does monotone decreasing mean? Well, it means ak is greater than or equal to ak plus 1. So it keeps getting smaller. Or sometimes maybe stays the same, but eventually gets smaller. And we will add a third condition where we guarantee that it's getting smaller eventually, and that's the limit as n goes to infinity of an is 0. As we talked about in previous videos, this is not enough. This is not enough for a normal series to converge, but it is enough for an alternating series, and that's what makes alternating series so interesting in producing proofs. So if this is true, then therefore, okay, all of this will imply that this limit of as n goes to infinity, s of n, this partial sum, this limit of the partial sum, it exists, and we can call that, let's say, big S. But also, and this is very interesting, the limit as n it goes to infinity of the even partial sums, this is also S, this exists, and the limit of the odds, this also is the same, and they exist. Of course, they all exist. So this is guaranteed by this alternating series theorem of Leibniz. Now, what's interesting about this is that sometimes it's easier to work with the even or odd partial sums rather than either one, like arbitrary. And that's exactly what we're going to exploit in this Euler-Mascheroni constant proof. Now, let me quickly review some results that I proved in the last video. Those results had to do with the harmonic sequence 1, 1/2, 1/3, so on, and the areas under the curve 1 over x. So here is the curve, y is 1 over x, and I have some points on it, 1 over 1, 1 over 2, 1 over 3. This is h1, and this is h2. These are the sequence in green, this sequence. And the areas that we're concerned with are these areas under the curve. So this, we're going to call this A1, and so on. And over here, let's say this is HN, and so we have AN is the curve area rectangle under this curve starting at HN. So this is going to be called AN over here. Over on the right here, I have plotted the area points. So this is H1, this is A1, H2, and A2, and so on and so on. This is HN, the green one, and AN is right below it. So you see that the AN is always less than HN. That's obvious from this curve. Here, if I multiply by 1, this width is 1. So the area of this rectangle is H1, and the area of this region under the curve is, of course, less. All right, so we proved that. And you can see here that the A's are always in between two adjacent H's, and the H is always in between two adjacent A's. Okay, that's a very critical thing, and we proved that in the last video, but let me write those results down. But first, let's make some room. Okay, let's try to keep this in mind. You can see all this action happening here. Just keep in mind, a green is in between two reds, and a red is in between two greens. We're considering the y coordinates. So we can express those relationships like this using these inequalities. We proved these in the last video. These are critical. This is what the present proof in this video of Euler-Mascheroni constant existence is based on. You can look at this video and or you can look at this graph here, and you can convince yourself using intuition that these things are true. Okay, just try that. Okay, that's an exercise. So as an exercise, try to see that these inequalities hold using the picture here. And once you're convinced that it is true, in the picture you can go to the previous video and see the rigorous proof of it being true. There are some other properties of these two sequences. If we look at these as sequences, HN as a sequence n is 1 to infinity, and AN as a sequence n is 1 to infinity, and then we have some properties that we should note. Okay, first of all, HN is bigger than 0, and also AN is always bigger than 0. Okay, that's property A. Property B, they're monotone decreasing. Both of them, HN is monotone decreasing, and AN is monotone decreasing. And as an exercise, try to argue why. It's fairly obvious because you have this here, so that can really help you. And finally, this property. The limit of both go to 0. And of course, the first one is pretty obvious. I'm sure you know that. But you try to explain why this one is true. So that's another exercise. I mean, it is obviously true. Just try to form an explanation. What would you say to somebody if they ask you, hey, why is the second one true? What would you say? Okay, and this is all really good. So it seems that we have sequences that satisfy A, B, and C, and we can use alternating sequence theorem now. Well, I'm not gonna use alternating sequence theorem on H or A. What I'm going to do is combine both of them to produce one sequence that has A, B, C properties, because if I just use one of these two sequences, it's not enough. I need to actually use both of them to get my Euler gamma. I need to use both of them. So I think it was Euler that actually came up with this proof. I'm almost 100% certain this is how he proved it. If you know otherwise, please let me know in the comments. But this is a very clever proof, and I guess Euler saw that gamma is kind of connects both the areas, because the areas have to do with logarithm, and okay, one over n that has to do with the harmonic sum and so on. And so he found a way to join both of these sequences into one sequence, and then exploited the alternating series, because just one of them isn't enough to create a relationship for gamma. All right, so let's see how to do that. We are now going to combine our H and A sequences to form a new sequence, G here. Here are my two sequences, and I will weave them together this way. Start with H1, then choose A1, then H2, choose A2, then H3, then choose A3, H4, then choose A4. And I claim that this sequence is going to work. It's going to have all the properties that I need. It looks like this when it's weaved together: H1, A1, H2, A2, H3, A3, and so on. And I can sort of write a mathematical expression for the kth term of G sequence. So it's HK plus 1 over 2 if K is odd. So, okay, the odds, let's see, this is K. So 1, 2, 3, 4, 5, 6. Okay, so odd is H. Yeah, 1 is H, 3 is H, 5 is H. So all the odds are H's and all the evens are A's. And the A, they are K over 2 if K is even. Let's see if this works. Let's choose an odd. All right, so K is 5. So that's this one here. So K is 5. K plus 1 over 2, that's 6 over 2, that's 3. So H3, yeah, it works. And let's choose K is even. K is 6. So K over 2, that's 3. I should get an A3. Yeah, that works. Yeah, okay, so this expression is good. So we have a complete picture now of this new sequence. And what we can do next is draw a graph of this and see what it looks like. This is a really cool picture, which I drew in asymptote. So let's have a look at this. So the red are the A's. So this is A1, A2. The green, well, this should be also green. The green are the H's, H1, H2, and so on. And the purple dots are the combined sequence. So this is G1, G2, G3, G4, and so on. So we see the horizontal lines, how it works. When G is odd, the horizontal line connects up with an H, with a term of the H series. And when G is even, horizontal line connects up with a term for the A series, and so on. Okay, so now looking at this graph, I claim that G has the following properties. First of all, GK is always greater than 0. Okay, and I think that's pretty obvious from this graph. GK is monotone increasing. That's something, decreasing, sorry, something I claim from this graph. And finally, that's the limit of GK goes to 0, and I claim that from this graph also. And I think that these things are obvious. Why are they obvious? Well, we should think back to just a few minutes before in this video. We have these very lovely inequalities, which kind of we deduced by looking at the graph, but we also proved rigorously in the previous video. And from these inequalities, these follow. You just have to sit back with a nice cup of tea and meditate on this a little bit, and suddenly you will have a mathematical satori, and you will see the light that this is true. These three follow from these inequalities. And we're ready now to apply the alternating series theorem, because we have all that we need as a prerequisite to the application of that theorem. Because the G sequence satisfies the prerequisites, well, I know now that the following alternating sum converges to a real sum. Yes, and it converges. This sum exists, and you can call it gamma. Yes, you guessed it. But not only that, we can look at the partial sums of these things, and they also converge to the same gamma. So the arbitrary partial sum converges to gamma. The partial sum having even number of terms converges to gamma. The odd partial sum converges to gamma. And the advantage of this is that I can now choose one of them, which may be more convenient to work with. And I'll choose that one. But as an interesting exercise, maybe you can choose the even one and see where that goes. I, in fact, have no idea what happens when you choose that. Why don't you give it a try and tell me in the comments. So let's try n is 4, let's say. So when n is 4, s of 2 times 4 minus 1, so that's s7. So it's 7 terms of this. Partial sum has 7 terms. So the first thing to note is that the a's are the things that have the minus sign. Okay, and let's see how this works. Well, n is 4, and the last thing is a plus 1 over 4. And if we think about this and try a few more examples, we see that these odd partial sums always end in 1 over n. So n is 4, so the ending here is 1 over n. So in general, I can write it like this. That's what your general odd partial sum will look like. Now, partial sums are finite sums. They are not like this up here, which is an infinite sum. And so because they're finite sums, I can do whatever rearrangement I want to them without worrying. So I'm going to separate out my harmonic terms from my area terms. There, that's all very easy to do. Just separate them out. Now let's examine this only. What are those areas? The area AK, this is from point 1 over k to here, 1 over k plus 1, like so. So in fact, this area, as we discussed in previous video, is integral from k to, here's k, and here k plus 1. From k to k plus 1, 1 over x dx. And this is log, okay, of k plus 1 over k. There we go. So this is a very interesting formula. And with this formula, then I can now express this whole thing into a beautiful compact form. All right, so this is log 2 over 1 plus log 3 over 2 plus dot, dot, dot. And the final one plus log, what's the final one? Kn, n over n minus 1. And I can now take all these things inside the log. 2 over 1 times 3 over 2 times, n over n minus 1. All this stuff here will cancel out like this, and I am just left with one thing, log n, like this. Very, very beautiful. And so my odd partial sum can be written like this. It's this harmonic sum minus log n. But we already know from before, from the alternating series theorem, this odd partial sum converges to gamma. All right. And so therefore we have the following very beautiful formula. There it is. This is the expression that defines the Euler-Mascheroni constant. There you go. I'm sure you've seen this before, but this is how you derive it. What an incredibly beautiful piece of classical analysis. Don't you agree? If you do agree, let me know in the comments. Tell me that, yeah, it's beautiful. Classical. No wonder Euler loved working with series and doing such calculations. It really is very, very elegant and beautiful. So now let's just look at this definition and see what it does numerically. I was curious to see how this thing works numerically, so I wrote some tiny little program in Maxima, which is a computer algebra system, to compute this for various n, and let's see what happens. When n is 10, the 10th partial sum is this. It doesn't look very close to gamma. If you recall gamma, I gave that in the thumbnail to this video, but it doesn't look all that close, but we have to go a lot higher before we get closer. 100th partial sum is getting there, but still we have a way to go. It only is able to get one decimal digit correct. Let's try 1,000. Yes, this is better. Now I think we've got 3. Let's compare it to the real gamma, see how many digits we got. Well, there's our gamma. That's the real thing. So we are able to get only 3 digits correct after 1,000 terms. Well, it's going to get there slowly, eventually get closer and closer and closer, but we're not guaranteed that it's getting there quickly. Well, that was really, really fun. And I hope you enjoyed this. Maybe some of you noticed that the last, let's say, couple of months of videos was sort of along this theme. This was the culmination of me talking about E and Euler gamma function, Euler gamma constant. And it was all building up to this. Of course, there's so much more to say about E and log and harmonic sum. I think I want to do Euler's proof about the infinitude of primes, which is related to this topic. Very similar ideas. Very beautiful proof. I think I might do that soon, maybe next video. And a lot of other analysis. But it was all culminating to this. I wanted to do this in great detail. This is a beautiful and amazing proof. And I think it's accessible to anybody in school, and it takes you outside. It transcends the normal school curriculum and shows you some stuff of great beauty and fascinating stuff that you unfortunately never see in school, because they have different objectives, a different set of things you have to study. You hardly ever see this stuff, but it's accessible to students, and it's beautiful. So with that, I will see you next time.